Ever wondered how EVs get from A to B? Is it essentially the same as an internal combustion car, but wired up to a giant battery? Or is there some altogether more subtle trickery afoot? Join us today as we pop the frunk and ask, how exactly do electric engines work? Surprisingly, the operating principle behind most modern electric vehicles predates the internal combustion engine by a number of decades. In 1834, a Dutch professor named Sibrander Strating of Groningen, Netherlands, built his own small electric vehicle. The catch being, its battery was non-rechargeable. Internal combustion engines work on the principle that fuel and air, when compressed and ignited, cause a tiny explosion. That's the combustion part. This explosive force pushes a piston. That piston's linear motion, in concert with a team of fellow pistons, transforms into rotary motion via a mechanical crankshaft. This in turn spins your wheels along the highway. Conversely, the fundamental principle that drives electric cars is magnetism. Everybody knows how opposing poles on a magnet attract and how alike poles repel each other. So let's imagine an experiment using two magnets, one fixed, the other mounted on a nearby rotating shaft. If the two poles nearest to each other on both magnets share the same polarity, say north to north, the magnet on the shaft will be repelled. Because it's attached to a shaft, the shaft will turn. That is until the south pole on the shaft magnet is aligned with the north pole on the fixed magnet, whereupon the shaft will again be still. In our imaginary experiment, we've made the shaft turn a half rotation. All very well, but that won't get us very far on the morning commute. Here's where electromagnetism enters the chat. In a fixed or permanent magnet, like the kind you have on your fridge at home, those magnetic poles are rigid and never change. North is always north, south is always south. On an electromagnet, however, which is essentially a core of metal coiled in electrical wires, this magnetic polarity can be reversed. Imagine one of our experimental magnets is now an electromagnet. If the south pole quickly flips over to north, the fixed magnet will yet again repel the moving magnet, rotating our shaft another half spin. That's a whole spin now. We're slowly getting there. For a basic illustration of how this polarity reversal works, imagine a very simple circuit involving a battery and a light bulb. Electrons flow in one direction from the battery, through the wires, to the light bulb, and back again to the battery. If we remove our battery from the circuit, flip it 180 degrees, then replace it in the circuit, those electrons will still flow around the circuit, just in the opposite direction. Either way, the bulb lights up. Electromagnets, like light bulbs, work whichever direction the electrons are flowing. But rather brilliantly, the polarity of the magnet gets reversed with the flow of electrons. So to keep our magnets in permanent repel mode, we just need to keep reversing the polarity of the magnet. How do we do that? One way would be to keep popping out the battery and flipping it around. But that's a lot